integrating trig. So let's go basically back the other way. Start off with, we're just looking at linear functions here, and then we can generalize. Well, we know that when we differentiate sine, we get cosine. When we differentiate cosine, we get negative sine. So this is where we've got to be careful, because therefore, when we integrate cosine, we'll get positive sine, but when we integrate sine, we'll get negative cosine. Going back the other way. And if it's a linear function, then it would just be 1 over a out the front. And then the other one, well, that's kind of easy. Ooh, sec squared. That just goes to tan. Hang on. So the reverse of the derivatives from yesterday. Personally, I haven't written it down here, just like all the other functions, I prefer to try and create derivative times the trig function and so on. But when it is a linear function, I suppose it is just easier to go 1 over the coefficient of x. So sine 3x then would be 1 over 3, but when we're integrating, sine goes to negative cosine. Angle, of course, does not change. Now, negatives and positives, got to be careful here. So the coefficient of x is negative, so it's negative 1/5, but cos goes to positive sine, so it stays as negative 1/5 sine of 1 minus 5x. Oh, and let's do a sec squared. And in this case, get a linear function, so 1 over a half would be 2, so 2 tan x on 2. Let's do a definite one. You'll notice when we're substituting in, they're in radians. Because calculus and trig, we deal with radians. So integrate sine 2x, well, 1 over 2, so there's a half. Sine goes to negative cos, and we're substituting in from pi on 6 to pi on 2. So we'll have minus half outside of the cos of pi minus the cos of pi on 3. Cos of pi, I don't know about you, even though it says pi, in my head I first of all send that back to degrees. I go, 180 degrees. Cos of 180, and then I think of my graph. Hang on, we start up here. Oh, that's negative 1. And cos of pi on 3, pi on 3 is 60. Cos of 60 is half. So minus 1, minus half, all of that times minus a half, 3/4. Find the volume of the solid formed when y equals the square root of sine pi x. Okay. We're going around the x-axis. So it's the integral of y squared dx. Oh, how lucky. That means the square root of sine goes. That worked out well. So we're just integrating the sine of pi x. But pi out the front as well. Coefficient of x in this case is pi, so it'll be 1 over pi. Oh, that cancels nicely with the pi. Oh, how lucky are we? Sine goes to minus cos, and we're going from 0 to 1. So in the end we have cos of pi, or negative out the front, cos of pi minus cos of 0, 2 units cubed, because it's a volume. Here's one where it's not a linear function. So what I was saying is, basically we want to try and create the derivatives, same as we really did with the exponentials, the logs, all those. So the derivative of x squared would be 2x. I've only got 1x, so to make it 2x, and divide by 2 out the front. So I now know that sec squared would go to tan, so that would be a half of tan x squared. Plus, of course, a constant. They love this question, or variations of it. Sine squared or cos squared, x, 2x, 3x, 4x, that bit doesn't matter. But the sine squared, because of course, you may remember last year when we did trig, and I said, hey, next year, remembering this relationship is going to be really useful when it comes to integrating. Remember, it comes from cos 2 theta, which of course is cos squared minus sine squared, but we could rewrite that as 1 minus 2 sine squared. Sine squared becomes the subject, so it's a half of 1 minus cos 2 theta is the result I want to use. And of course, if it was cos squared, the only difference is it's 1 plus cos 2 theta. Back to our integral. So that becomes a half of 1 minus cos 2x, and both of those things we can handle. 1 goes to x, of course, and then cos, it's a negative cos. Cos goes to positive sine, so it stays as negative a half, in this case, sine 2x. Whether you leave it factorised or expand out, I guess it's up to you how you want to write that final answer. Tan x. But of course, to do tan x, we rewrite tan. Sine on cos. And we now have the situation, almost, of derivative on function. Derivative of cos is not sine though, it's negative sine. So we need to balance that out. I now have derivative on function, so it's minus the log of cos. Personally, I don't remember it as minus the log of cos. I bring the minus 1 into the log and use it as a power. And so it's cos x to the power of negative 1, which means 1 over cos x, which is... So another way we could write it is the log of sec, and that's how I tend to remember it. And that's how you should too. Well, not necessarily log of sec. You could remember minus log of cos, but you don't need to go through that process every time. It's what I call the non-standard integrals, the ones they don't give you, but are well worth knowing, because it's just going to save you time. So integral of tan, the log of sec, or if you prefer, minus the log of cos. Ooh. Cos x sine to the power of 7x. Okay, this is going back to the idea of derivative times a function to a power. We have a function to a power. That function is sine. So what I'd like in front of that function to the power is the derivative of the function. The derivative of sine is, so we actually have it. So here I can just add 1 to the power over the power. Now, if you don't see that, we can do it via a substitution. Again, we'll see this technique in more detail later on this term. But we'll make u, well, basically what's causing me the problem, sine. That's to the power. So u is sine x, du is cos x. Of course, that means I've got to change the limits if I'm going to do it this way. And so when x is 0, u is 0, x is pi on 2, u is 1, and it simply just becomes u to the power of 7. Add 1 to the power over the power. There we go, 1/8. So you can do it by substitution. In reality, I probably would have looked at that and said, oh, derivative times function of the power. Okay, add 1 to the power over the power, sine to the power of 8 over 8. You still would have got the same answer. 14I, 14J.